Okay, now that we've perfected the multiplication properties of exponents, let's go ahead and look at the division property of exponents. So looking at this first one, it says that we're supposed to simplify 7 to the 8th over 7 to the 3rd. Let's go ahead and look at it as a factor. We understand that 7 to the 8th means that we are multiplying 7 8 times. 1, 2, 3, 4, 5, 6, 7, 8 times. And then we understand that 7 to the 3rd means we are multiplying that 3 times. And we understand that this is written as a fraction, but that is a division sign. Okay, now let's go back to what we know about when we do look at this as a fraction. We can go ahead and cancel out like factors. So these two 7s cancel, these two 7s cancel, and these two 7s cancel. Remember, if there's nothing in that denominator, we realize that we're still multiplying by a 1 down there. So what do we have left over? 7 to the 5th over 1, or just 7 to the 5th. So we're supposed to simplify this as a power of 7 to the 5th and a numerical value. So with calculator out, let's look at both sides of this. I'm going to put parentheses 7 to the 8th, and I'm going to divide that by 7 to the 3rd. What do I get? 16,807. Is that the same as 7 to the 5th? Yes, it is. So we know that that did work. And of course, I just forgot that. 16,807. Okay. Now let's look at what we did. How did we get, what did we do to 8 and 3 in order to get to that 5? It looks like we took and subtracted. So 7 to the 8 minus 3 is 7 to the 5th. Okay, let's try that one more time and see what happens. Again, 5 to the 6th. We see that power is telling us to multiply that 5 6 times. And we are dividing that by 5 squared. Again, we are going to cancel like factors. We end up with 5 to the 4th. So is that the same thing as 5 to the 6 minus 2? Yes, it is. Okay, so again, we're starting to realize that when we are dividing exponents, we keep the base and we subtract. I'm sorry, when we are dividing powers, we keep the base and subtract the exponents. So we are going to say that this is 5 to the 4th, which equals 625. Okay, so what is the rule? We are going to say over here in the corner, when dividing powers, we keep the base and subtract exponents. Okay, remember that when we were dealing with multiplying, I did stress the keep the base. Same thing here. Some students want to see this as 1 to the 4th. So many times they get 1 as the answer because 1 to the 4th is just 1. That is not true. We keep the base, we subtract the exponents. Okay, so with that in mind, let's go ahead and look at this next one. We have 3 squared, and we are dividing that by 3 to the 5th. So we're going to look at this part first. We decided that we are dividing powers, so we are going to keep the base, and we are going to subtract the exponents. We'll look at what 2 minus 5 is. It's actually a negative 3. Okay, is that the same thing as 3 to the 3rd? I'm not quite sure, so let's go ahead and go one step back and look at 3 squared and divide that by 3 to the 5th. Okay, then let's go ahead and cancel out like factors. Okay, nothing left here in the numerator, but remember, there's always that 1. So how do we simplify this? We have just a 1 left over in the numerator, and we have 3 to the 3rd in the denominator. So look at this. 3 to the negative 3rd is actually 1 over 3 to the third. Okay, so there's our power. What is that as a numerical value? We're going to say 1 divided by 3 to the third. We're going to ask for that to be a fraction, and they tell us 1 over 27. Is that the same thing as 3 to the negative third? Yep, it is. So either way, our answer is 1 over 27. So what does that negative mean? Let's go ahead and look at this one more time. 4 to the 5th divided by 4 to the 9th. So I have 4 to the 5th. I know that I am dividing, which means I keep my base. I subtract my exponents. And again, I end up with 4. I end up with a negative exponent. So writing this out, I'm multiplying by 5 and I'm multiplying by 9. And I cancel like factors. Okay. 4 groups of those 4s, nope. 5 groups of those 4s cancel. I'm left with 1 over 4 to the 4th. So there's my positive power, because notice that word positive did show up. I can't leave it like this because that's a negative power. So in order to completely simplify, I have to flip it and make it a positive power. What is 4 to the negative 4th? As a fraction, 1 over 256. Okay, so this equals 1 over 256. So what does that mean about negative values, negative exponents? Okay, well, we said when you have a negative exponent, what happens? It looks like 4 to the positive 4 is 256, but this is in the numerator. So what happens is it flips. When you have a negative exponent, write the reciprocal, because when we flip, that's what we're doing. Write the reciprocal and change exponent to positive. Okay, is that what we did right here? 4 to the negative 4th. We wrote the reciprocal of that, of 1 over 4, and then we changed the exponent as a positive. Write the base reciprocal. Write the base reciprocal and change the exponent to a positive. So with that rule in mind, let's go ahead and look at this next one. 2 to the negative 1. Again, there's our negative exponent. What are we supposed to do? We're supposed to write the base reciprocal. So this is 2 over 1. So I'm going to flip that, 1 over 2. Then I'm going to change that exponent to a positive. So 1 over 2 to the first is actually just 1 over 2. Okay, same rule. Simplify 5 to the negative 2. I see that negative exponent. That means that I'm going to look at this 5 over 1 and I'm going to flip that. I'm going to make it 1 over 5th. I'm going to change that exponent to positive, so I understand that that's actually 1 over 25. So two concepts that we learned there, that when we are dividing exponents, we are subtracting. When we are dividing bases, we are subtracting exponents. We also realize that when we have a negative exponent, in order to completely simplify that, that does have to be a positive power. So we flip it, we make that exponent positive. We're actually going to look at one more problem down here. I want to see what happens if I have 5 to the third over 5 to the third. Okay, so we have said that we are dividing bases, we are dividing powers. So I'm going to leave the base and I'm going to subtract the exponents. Well, what's 3 minus 3? 0. So I have 5 to the 0. What is that? All right, let's go ahead and look at what that is. I have 5 times 5 times 5. I'm dividing that by 5 times 5 times 5. Well, what happens to everything? All of my factors cancel. What am I left with? Well, remember up here, we're always left with a 1. We are always multiplying by a 1. So what's left over in the numerator? 1. What's left over in the denominator? 1. What's 1 over 1? 1. Okay, so 5 to the 0 is actually 1. So one more rule that we have to know is that any term to the 0 power is 1. Doesn't matter if it's x to the 0, if it's 1 million to the 0 power, any term to the 0 power is 1. And this is the reason why. So don't think that 5 to the 0 is 0. Any term to the 0 power is 1. Okay, so a couple new concepts. Let's go ahead and give these a try in the notes and vocab. Okay, objective is same as last section with a couple different concepts. We're applying the rules of exponents in those numerical expressions. So we can go ahead and simplify them. They show a couple other good examples of what we did in the introduction of understanding that quotient of powers rule, that again, when we are dividing bases, we are subtracting those exponents. So with that in mind, we're looking at example 1. It does say assume that no denominator equals 0 because we understand that we cannot have a 0 in the denominator. So that's just what that last section is, just to kind of cover all the bases. So two different pieces here. We're dealing with G's and we're dealing with H's. I know that I'm going to keep my base of G, and I have a 3, and I'm subtracting a 1. I know I'm going to keep my base of H. I have an exponent of 5, and I'm subtracting 2. So final answer, I have G squared, and I have H to the 3rd. Remembering that there is a little 1 on our G right there. Okay, keep the base, subtract the exponents. Numerator minus the denominator. All right, go ahead and give that a try in guided practice 1. Okay, making sure that we know that y to the power of 1 is in that denominator, we go ahead and kept our bases, subtracted our exponents. We do just get x to the power of 1, so a lot of times we don't put that 1 in there. We just know that it's x, and that power of 1 is given, y to the 3rd. Looking at 1b, we have 3 pieces, but still we went ahead and subtracted them. Look at what happened to the piece. P to the 1 minus 1 is p to the 0. We just decided that that means 1. That doesn't mean p to the 1, that means just 1. So when we look at this, our final answer is k squared times n to the 7th, because that p to the 0 does show up with that given multiplied by 1 out here. Okay, don't keep him in the problem. He is technically there in spirit when you look at that times 1. All right, looking at that product of power rules, which is what we dealt with multiplication. Again, what that means is that 4 affects everything in the numerator and everything in the denominator. So power of a quotient, it's going to affect all pieces. Okay, with that in mind, let's look at example 2. Again, now that we're dealing with quotients, we really have to be careful with what happens to that 2. We understand it affects all pieces. So there's a constant of 3, there's a power, and there's a denominator of 7. So we have to look at all 3 of those pieces. We have 3 squared. We have p, power to a power. What we learned last section is that we are multiplying those. And then we have 7 squared. So simplifying that, 3 squared is 9, p to the 6th over 7 squared, 49. Simplified. So again, that power affects all terms or all pieces of that term. Okay. All right, go ahead and try guided practice 2. Okay, there they are. Check your answers with mine. Once we get to 2C and 2D, realize that we have 4 things that exponent affects, 4 pieces of our term. So do make sure that you get all the way over to that 3 So that 3 squared turns into 9 in the denominator. Okay, so stay organized, stay focused, make sure that you're following all steps. Okay, we also talked about with the quotient of powers that anything to that 0 power equals 1. It doesn't matter what we're looking at, if we're looking at a constant, if we're looking at variables, or if we're looking at a fraction. Anything to the 0 power is 1. So let's look at this huge ugly mess with example 3a. There's a lot going on in there. But notice this very big parenthesis. Notice that power of 0 out front. That means that 0 affects every single piece in there. So without having to draw all of those crazy arrows, I know that basically by default, my answer is 1. It's a little bit different with b, because look at where that power of 0 is. It only affects y. So when I rewrite this, this is x to the 5th. I am multiplying it by y to the 0, which I know is 1, divided by x to the 3rd. So I know that that is x to the 5th over x to the 3rd. Well, look at this. This is a quotient. So I know I keep my base. I subtract my exponents. Final answer, x squared. So understanding anything to the 0 power is 1. Understanding how that affects a problem. Does it affect the whole problem or just a piece of the problem? And you'll have to find that out with guided practice 3. Okay, check your answers with mine. On 3a, the only thing that 0 power affected was my d, which turned into 1. Okay, I realized that I had 2 quotients going on there, so I did subtract both my b's and c's, ended up with b squared times c. On 3b, that power of 0 affected everything inside that parenthesis. So again, instead of showing all of those arrows, I realized that they all simplify down just to 1. Okay, next part of this section deals with those negative exponents that, again, we realize what happens with them, that if we do have that negative exponent, we are going to have the reciprocal of that. So they show another example just to review. 2 to the negative 4, we flip that. That 2 turns into the denominator. Our exponent becomes positive, so it's actually 1 over 16. Okay. Other way around as well. So look at this example, that if our negative exponent is in the denominator, when we flip that, that variable turns into the numerator. So keep that in mind too. And with that, let's go ahead and look at these problems. Okay, when there is a lot of negatives going on in a problem, what I tell students to do a lot of times is just to draw a line. And then what we're going to do is we're going to fill in the blanks as to where all of these pieces go. So let's look at this n to the negative 5. This is in the numerator, which means it has to flip to the denominator with the positive 5. Let's look at this p to the 4th. It is in the numerator. It is positive. So it stays in the numerator. Let's look at this r to the negative 2. It is in the denominator. It is negative. So it needs to move to the numerator and become positive. Okay, so negatives, they have to switch positions. If it's numerator, drops to denominator. If it's in denominator, it moves up to numerator. Final answer, because we cannot simplify any of those. Okay, all right, let's look at this next one. It does look like we can do some simplifying here, so I'm going to go ahead and look at each piece separately. I'm going to look at my constant coefficients. I'm going to look at my variables. And we're going to see what happens here. And then I'm going to look at my u. Okay, so first off, I'm going to go ahead and just simplify and see what happens here. I have 5 over negative 20. That, again, is a fraction. So that simplifies down to, you know what, actually, I'm going to draw a line. Did I use green? I did. So I'm going to draw a line. And what I'm going to do is I'm going to fill in the blanks here. Because 5 over negative 20 simplifies down to 1 over negative 4. So I have a 1 in the numerator. I have a negative 4 in the denominator. Now I'm going to go ahead and look at r. I have r. I am dividing. So that means I'm going to take my exponents and I'm going to subtract them. So what do I end up getting? Negative 3 minus 2 is a negative 5. since that's negative, and this is technically the numerator, he has to drop to the denominator and become positive. All right, now let's look at our t's. We have t to the 4 minus 7, which is t to the negative 3. This is the numerator because this is a positive number, which means that we have to drop, since he has a negative exponent, he drops into the numerator. Then let's look at our u. Technically, this u is 1 over u to the negative 5. Negative exponent. He is in the denominator, so he moves up to the numerator. Okay, really focus on each piece, trying to figure out what we're doing. When we subtract like this and we get an answer, this is automatically numerator. So as soon as you see that negative, flip him down to the denominator. This is a little bit different because that u started in the denominator. We had nothing to subtract him from. So that's why he moved up. Okay, there is one answer down. Now let's go ahead and look at this next one using those same concepts. So again, we have all of these different pieces that we have to deal with. One at a time, we should be able to make it through this. And I would highly recommend drawing that line, understanding what that line does and where to put, oh my goodness, put all of those pieces. Okay, so here we go. Here's our line. I'm going to look at those constants first. I have 2/10. I know that that just simplifies down to 1/5. We have to just look at that as a fraction. That is not 2 minus 10. So I have the fraction 1/5. Then I'm going to look at my a's. A to the 2 minus a negative 3. What happens to my a? He is actually positive. So an a squared divided by an a to the negative 3 is a positive a to the 5th. So he is the numerator. Now let's look at our b's. Okay, we have b to the 3rd. We are subtracting a negative 1. He becomes positive b to the 3 minus the negative 1. Positive b to the 4th in the numerator. Last one, c. Negative 5 minus a negative 4. C to the negative 1. So he is negative, which means that he is going to drop to the denominator a positive power of 1. So the two pieces that we technically don't need in this problem that I am going to get rid of is this one here and this one here, because we know that they are given. Okay, so that then would be our final answer. Do these take time? Yes, they do. Do they take organization and focus? Yes, they do. So focus on guided practice 4. Okay, let's see what you've got. A couple of things on this first one. Notice that our w's do disappear, so that actually turns into 1, who shows up right there. Okay, we have an x squared. The y was in the denominator, so he flips to the numerator. The v was in the numerator, so he flips to the denominator. So final answer, x squared y to the 6th over v to the 3rd. Tricky concepts on here, remember all of those negative signs. So with this, we had c to the negative 4 minus a negative 2. So do remember all of those. Remember what that does to our problem. Again, c to the negative 2, he flipped to the denominator, b to the negative 2, denominator, a to the negative 11, denominator. Okay. And again, pretty straightforward on this one. I do simplify, trying to get rid of any not needed that we know that we don't need, like the 1 in the numerator, the 1 in the numerator here. So yes, a lot of different steps, but I think we can handle it. Okay, one last concept that we have to talk about is called order of magnitude. It says the order of magnitude is used to compare measures and to estimate and perform rough calculations, very rough calculations. We need a quick, simple estimate. And so some of these, yes, are going to be very rough. It says the order of magnitude of a quantity is the number rounded to the nearest power of 10. For example, the power of 10 closest to 95 billion is 10 to the 11th, or 100 billion. So the order of magnitude of 95 billion is 10 to the 11th. Okay, we want to have a nice base of 10 so we can compare everything, because when we have the same bases of 10, then we can go ahead and either add our exponents or subtract our exponents. Okay, so with that in mind, again, very rough estimates, whatever it is, the power closest to 10. So suppose the average height of a man is about 1.7 meters and the average height of an ant is 8/100,000th of a meter. How many orders of magnitude as tall as an ant is a man? So when we look at this, how many orders we are comparing the man's height to the ant's height. Okay, so we are comparing 1.7 to 0.008, but again, when we are dealing with orders of magnitude, we want to figure out what power of 10 this is the closest to. This is closest to 1. Okay, what is this closest to? This is actually closest to 1/1000th. So we are going to write that as 1/1000th. Okay, so we're getting closer, but we want that as a power of 10. So what is 1 the power of 10? Remember, anything to the 0 power is 1. So we have to write the man's height as 10 to the 0 power. Strange, but remember, that's a fancy way of actually saying 1, which is close to what his height is. How do we write 1/1000th? Well, knowing what we know about scientific notation, we know that this is actually 10 to the -3 because we would move that decimal over. Okay, so we're getting closer. Now we actually have something that we can compare. We have 10 to the 0 over 10 to the -3. We know that means we keep our base and then we subtract our exponents. So what is 10 to the 0 minus -3? 10 to the third. What does that mean? Again, we are comparing their height. So 10 to the third is 1,000 times taller. Order of magnitude. A little bit hard for some students to comprehend, to realize, well, why is 1.7 simplified down to 1? Because we need a base of 10. We need a very quick estimate. If we didn't have a calculator and we needed to figure that out, we could go from there. Okay, we're down to guided practice 5, so go ahead and give orders of magnitude a shot. Okay, this is a pretty nice problem because they actually gave us those orders of magnitude. We didn't have to go find them. But they give us Earth, they give us Milky Way. We are comparing Milky Way to Earth. So I set up their orders of magnitude. I realized I subtracted them. 44 minus 17 is 17 times as big the Milky Way is to Earth. So orders of magnitude, pretty high concept. I don't think that you're going to see it, but if you do, use these steps. Get that base of 10 so we can quickly compare them. Okay, so I think we're ready for the assignment for this.